Okay, so yesterday I was talking about the state space representation of dynamic systems. The state space representation can be used for both nonlinear and linear systems. So that's one thing that makes it different from the transfer function approach. Transfer functions are only used for linear systems. So if you have a general nonlinear dynamic system, you can write it in state space form. But of course, if your system is linear, the state space form gets even better. So it gets very nice properties for linear systems. Okay, so if you have a general dynamic system, a linear dynamic system, then you define your state variables, and while defining state variables, you need to make sure that all these terms are represented somehow in your state equations, and then you write state equations out of your state variables, where state equations are the first time derivatives of your state variables. And if your system is linear, everything can be written in such a nice matrix form. Okay, so your state equations become a linear function of your state variables and your input signal. And the good thing here is there are no differential terms on your state equations except the first derivatives of your state variables. Okay, so there's nothing, no derivative term on the right hand side of your state equations. So as an example to that, let's take a look at this example. So by the way, in your second midterm exam, there will most definitely be an application of this. So you will be required to either write a state space model for a given transfer function or for a given differential equation. So this is going to be a very good example for the second midterm. This is a second order system, and it is given in this form. So if you look at the right hand side, there are some derivative terms of the input signal as well. Okay? Okay, and this is the highest order of differentiation on the output term is 2. M is 2 as well, because we have the second time derivative of input. So if you remember our yesterday's lecture, this means that we need to use two state variables since n is equal to 2. And these state variables should be defined such that they include all these terms, y dot and u dot. Okay, so if m was 0, in which case there was no derivative terms of the input signal, then we don't need these two terms. So we define the state variables only using y and y dot. So this is a more complicated example. So let's take a look at this one. So here's a nice procedure for choosing the state variables. So they should include all these terms, but if you just define them arbitrarily, you may not get a solution. To get a solution, you need to follow a systematic approach. So this is such an approach that you can follow. So we start with this equation and collect all derivative terms on one side. Okay, so this is a second derivative of y, first derivative of y, and these are the derivatives of u. All of those terms are collected on one side, and on the other side we are left with no derivative terms. So I call these derivative terms x2 dot. So here's how I define my second state variable. I define my second state variable such that its time derivative is equal to all these terms here. So that means the x2 itself should be integral of that. And here's how I define x2. If I integrate y double dot, becomes y dot plus ay minus cu dot minus du. Okay, so this is my second state variable. Next, I collect all the derivative terms in the x2 expression together, and I define my first state variable such that these derivative terms become the first derivative of my first state element, first state variable. So I call this x1 dot, and then x1 is the integral of this part. So that means x1 is equal to y minus cu. Okay. Now I have defined my state variables. My first state variable is this. The second state variable is that. So if you look at these two equations, you will see that they in fact include all these terms. Okay, now these are my state variables. I need to obtain state equations, and state equations are the derivatives of these two state variables. So I differentiate these equations. First, I differentiate the first state variable, x1 dot is equal to y dot minus cu dot. Okay, but if I go back here, this is y dot minus cu dot. So I can write. So I need to make this a state equation, right? So that means the right hand side should include x1, x2, and u only. There should be no other terms. And that equation is obtained from here actually. So I write y dot minus cu dot as x2 minus this part. X2 minus ay plus du. So this is still not a state equation. Even though there are no derivative terms, I still have y. So there should be no y here. There should be only state variables. And to get rid of y, I use my first state variable. So instead of y, I write x1 plus cu. Okay, so this is equal to y. And after doing that, this turns into a valid state equation. Okay, so this is equal to y. And then I collect x1 and x2 terms and u terms together. So this is the first state equation. It only includes x1, x2, and u. No derivative terms, no y's. I obtain the second state equation by differentiating the second state variable. x2 dot gives me this. And if you remember how x2 was defined in the first place, this was chosen to be x2 dot. Okay, so now x2 dot is equal to actually this part, eu minus dy. Eu minus dy. And again, I need to get rid of the y term. And I do that by inserting this instead of y. And that gives me the second state equation. This is equal to y. And if I open that parenthesis, the second state equation becomes minus b times x1 plus this times u. Okay, again, this is a valid state equation because there is no y, no derivative terms. Okay, so if I collect them together, this becomes the state space model for that system. So these are the two state equations, and this is the output equation. So this model gives or represents the original system exactly without any approximations. So that's exactly equal to this model. Okay? So this is just one way of defining state variables for such a system. And as I said several times already, the state space model is not unique. So you can have a lot of different state space presentations for any given system, and this is just one of them. Okay, so and you can take this and write it in matrix form, which is this thing. So this is the X vector, A matrix, B matrix, C and D matrices. So this is the state space model. Okay. So as I said, in your second term exam, you will have a question regarding this procedure. So I will ask you to obtain a state space model for a system. Well, sometimes I let you choose your state variables, and sometimes I give you the state variables myself and ask you to obtain the model for those state variables. Okay? Any questions? Good. Now let's start talking about linearization. So this is a very, very useful concept and very a procedure that we apply very frequently. So if you want to work as a controls engineer, you will definitely have to do this a lot. So you will be required to linearize different systems all the time. Bir yerde bir şey yazmıştı. Nerede yapmıştık ya? Okay. So, as you know, state space representation can be used for both nonlinear and linear systems. If you have can be used for both nonlinear and linear systems. If the system is nonlinear and time invariant, state space equations are in the following form. So for a nonlinear system, we have the state equations as a vector differential equation. X dot is equal to f of x and u, and then the output is another nonlinear function of x and u. So these are the state equations. If the system is linear and time invariant, state equations are in the following form. We can write this in the matrix form as x dot is equal to ax plus bu. So here we have, so these are linear functions of x and u, whereas these are nonlinear functions of x and u, right? X and u, and they are very nice or very well developed theories that are applicable to linear time invariant systems. So if you have these set of equations, then using these A, B, C, D matrices, you can do a lot of different things. You can design controllers, you can check robustness, you can check system dynamics, you can do all sorts of things using these matrices. Okay, but for this is pretty much nothing. Well, there are certain things that are applicable to nonlinear systems, but we don't have such general rules applicable to all nonlinear systems, because these nonlinearity can be due to a lot of different things. It can be due to trigonometric functions, or it can be due to quadratic functions. You may have terms like y squared, y to the power 3, or it can be due to friction. And all of these nonlinearities has to be treated differently. So you don't have a theory that can be applied to all nonlinear systems. So if you can somehow make a model that is linear, which resembles the original nonlinear system somehow, then you can use this approximate model for the original system. Obviously, you cannot express the original system exactly with a linear model. So this linear model can only be an approximation at best. Okay, but still, if you can find such a nice approximate linear system that looks like the original system, that will be very, very useful. So that is what is done in linearization. So in linearization, we somehow find approximate linear functions of x and u that resembles this original nonlinear function. So this is what we want to do. We want to get this original system and find a linear model that will look like the original one. And for this, we use Taylor series expansion. So as we will see now, the Taylor series is a very, very powerful mathematical tool. And I'm sure you've seen Taylor series before, right? I don't know where, but you must have somehow at some point seen the Taylor series. Bu Taylor serileri çok beni şey yapıyor, hayrete düşüyor. Yani pek çok şey hayrete düşürüyor da Taylor serisi onlardan biri. Taylor serisinin ne olduğunu biliyorsunuz değil mi? Okay, so let me just copy these things. Gerçi ben çok kolay şaşıran bir insanım. Yani şu kalemin burada bunu yazması bile hala bana çok amazing geliyor. Ama bu Taylor serisi hakikaten güzel bir şey. Okay, so let's say you have a nonlinear function f of x, and you know the value of the function and the value of its derivatives at a constant point. Okay, so let's say there's a point x0, and at that point x0 you have the values of all these quantities, the value of the function itself, the value of its first derivative there, its second derivative, third derivative, nth derivative, and all the derivatives up to infinity. And you only need to know these values at one point. So if you have, let's say x is a scalar, and your function looks like this. It can be anything, right? So this is f of x. And let's say this is your x0 point. Okay? And you only have information at this point and nowhere else. So this is the value of the function f x0. Its first derivative is the slope at that point, right? So this is the first derivative. This is df by dx at x0. And then the second derivative, third derivative, fourth, all derivatives up to infinity. And if you have all these values, then you can write this series. And this series tells you that the value of the function at any point besides x0, so let's say the x is chosen somewhere here, so this is the x point. The value of the function at this point can be constructed using all the values for the x0 point. So you take the value at x0, fx0, and then you add to it the value of the first derivative times x minus x0, where x minus x0 is this distance, right? This is x minus x0. And then you add to it the value of the second derivative at this x0 point and multiply it with x minus x0 squared by 2 factorial. And you continue all the way up to infinity. And that way, believe it or not, you can find the value of the function at this point. So you can eventually obtain this value. This is f of x. Ya bu işte çok bana inanılmaz geliyor. Yani orada 10 kilometre uzakta bir tane nokta var. ve 10 km uzaktaki noktayı şu anki bulunduğum noktadaki türevlere bakarak hesaplayabiliyorum. Yani üşenmedim, denedim, bir sürü örnek çıkardım. Böyle terim ekledikçe yaklaşıyor. Wikipedia'da bunun animasyonu da var. Ki ben kendimle uğraştım, böyle animasyonlar falan yaptım MATLAB'te. Ve terim ekledikçe benzemeye başlıyor. Şimdi ilk if you look at what this Taylor series is, it's nothing but a polynomial, right? And by adding terms to the Taylor series, you're increasing the degree of the polynomial. X0 plus okay, so this is the first order polynomial in terms of x, right? Because we just have x, and this is a constant number. This is a constant number. This is a constant number, and I just have x there. If I add the second term, now this is a second order polynomial in x because I have this x squared term here, and every time I add a term to this Taylor series, it increases the degree of the polynomial. So if you just use one term, this is a constant number, so it's a zeroth order polynomial. If you use the first two terms, it is a first order polynomial, second order, and usually we write higher order terms. So the idea is the first two elements in the Taylor series expansion give you a first order polynomial, which is a linear function, right? So this gives a linear function in x. So if you take the Taylor series expansion and only keep the first two terms, the first order polynomial, in x, which is a linear function of x. If you add the next term, that comes a second order polynomial, which is what we call a quadratic function, because it includes the second power of x. So this is the idea of linearization actually. So we take our nonlinear state equation and apply the Taylor series expansion to that. And the Taylor series expansion, we only take the first two terms in the Taylor series expansion and then ignore all the other terms in the expansion. Obviously, since all these terms are ignored, this linear model is only an approximation. It can never give the original system behavior exactly. But there's a very nice property of this expansion. This is the first term we ignore. It has square of x minus x0. The following term has the third power of x minus x0, right? So let me just write it here. So if x minus x0 is a small number, then these high powers of that will be negligible anyway, right? So if let's say x minus x0 is 10 to the power minus 1, 0.1, then its square will be 10 to the power minus 2. This will be 10 to the power minus 3. That means whatever these constant numbers are, their contribution will be negligible if and only if x minus x0 is a small number. Okay? So that means if this is your nonlinear function, you can, if you want to predict the value of x here, the value of function here, then you need to have a lot of terms in your Taylor series expansion. But if you are only interested in a very small neighborhood around your x0 point, then the linear approximation will work just fine. Bunu daha önce bir grafik üzerinde göstermiştim. Yani ne kadar karmaşık görünen bir eğri olursa olsun bir nokta seçin ve o noktanın çok yakınına baktığınız zaman o bir düz doğru haline geliyor. Ve o noktada da en azından o baktığınız küçük bölge içerisinde o doğrusal model size çok yakın bir sonuç veriyor. Yani linearizasyondaki şey de bu. Ana fikir bu. So normally by linearizing a function you get an approximation, but the approximation is very very accurate in a very small neighborhood around your linearization point. So okay, you can read through all of this later. Okay, so let's try that again. So let x be defined between -1 and +1, and let's consider a polynomial. This is going to be a fifth order polynomial, and so this is just some random fifth order polynomial I created. So this already looks pretty smooth, but if I choose any point, let's say -0.6 is the point where I want to linearize this function, and if you zoom in around that point, you will see that what you see is exactly a line anymore, right? This is not a curve anymore. This can be represented by a first order polynomial very well. So that's what I meant. Okay, so how do we use this for linearizing systems? We take these original nonlinear state equations, so to linearize nonlinear expansion, we take the nonlinear state space equations for that system, which are these equations, and then we apply the expansion to these nonlinear functions. Well, different from what I wrote before, these functions are functions of two arguments, right? Instead of just a function of x, it's a function of both x and u. So here's how you do the Taylor series expansion for such systems. You first, then we apply Taylor series expansion to the nonlinear f and g functions. For the expansion, we need to choose a base point x0 and u0. The expansion is performed over or around that point. So the value of the function at that base point x0 and u0, and then I use partial derivatives. First I differentiate with respect to x and evaluate the value at that base point, and then multiply it with x0 plus, now I differentiate, take the partial derivative with respect to u now, u minus u0, again this should be evaluated at the base point x0 u0, and then I need to do it if I need the higher order terms, but now I'm just going to call them higher order terms because all I need is the first order terms. And this is x dot. Now, since this is a vector equation, so f is a vector function, so while taking the derivatives, you need to take derivatives accordingly, appropriately. So that means this term, well, first, before that, let me say that f function is a vector function. So f of xu has n functions, f1 xu, f2 xu, and fn xu. So if you want to take the partial derivative of this function with respect to x, in the end you get a matrix, right? So the partial derivative of f with respect to x is actually a matrix, and that matrix is the following. You differentiate the first function with respect to the first state variable, because x is itself a vector, right? Then you differentiate that first function with respect to the second state variable, and you do this for all the state variables for the first function. You repeat this for the second function, and then you repeat the same thing for all the functions up to the last one, fn del x1. And you evaluate everything here at the base point x0 and u0. Okay, so normally this is n by n matrix of x and u, but when we evaluated x0 and u0, becomes a constant n by n matrix. So we have a similar situation for this derivative term, del f by del u. Bunlar şurada vardı aslında, değil mi? So this partial derivative with respect to u becomes a vector. If you have a single input, then you have to differentiate all these n functions with respect to u. But if you have more than one input, then that P becomes a matrix as well, in which case and this is if u is a vector itself, u1 up to up. Okay, so that means we can write it as this is an n by n constant matrix, and if we call that A, this becomes A. and if we call this delta x, that becomes delta x. So similarly we call this part b. We call this part delta u plus higher order terms. And this is not an exact equality anymore. At this point, this is an approximation once we get rid of the higher order terms. Okay, so do you think this looks like a linear state space model? It does, right? It has this term, ax, bu, but there's this term here, and this is not quite in exactly the same form as we want. Okay, so we want that to be in exactly this form, x plus bu, and yet here we have this thing, and this, because of this thing, this is not really a linear model anymore, because if you think about the superposition principles, then this will ruin that, destroy the superposition property. So we need to get rid of this term, and this and hence linearity, and we can get rid of that by choosing x0, u0 such that that function is equal to 0. F 0 is equal to 0. So in other words, we want x0, u0 such that this becomes equal to 0. Bunu hatırlıyor musunuz bilmiyorum, but this is the definition of equilibrium point. Yani denge noktası diye bir şey tanımlamıştık. Denge noktasında şey demiştik. Tüm sistemdeki türevlerin sıfır olduğu nokta demiştik. Sistemin dengede durduğu nokta. Eğer bu x0 ve u0 ve sistemin dengede durduğu nokta olarak seçersek, o zaman bu terim sıfır oluyor. So if you choose this base point as an equilibrium point of your system, then define a new state vector as and the new state vector equation becomes x new dot is equal to delta x dot, and that's equal to x dot minus x0 dot, but this is 0 because it's a fixed point. So after all of this, we end up with a linear. This is equal to 0, so I just remove that. So these are new state variable and okay, so this is in exactly the same shape and form as a linear state space model given by these equations. Well, it's the first one, but the same thing is done for the second function as well. Okay, so our time is over, so let me stop here and I will continue from here next week.